Okay, for what we have in the first problem, we're looking at solving for the differential equation dy over dx is equal to 9 minus x. So for what we have in terms of the setup, again we have dy over dx equal to 9 minus x, and this is a differential equation where we can separate the variables and the differentials. So what we can do is that we can separate dy from dx, multiplying the equation on both sides by dx, and in this case we have that dy is equal to the quantity of 9 minus x dx. And upon separation of the differentials, we can integrate on both sides. Okay, so we have for the antiderivative of dy, that becomes y, and we have for the general solution of y will be the antiderivative of 9 minus x dx plus a constant, and thus we end up with y is equal to 9x minus 1/2 of x squared plus c. In the case of what we have for item number 2, a problem fairly similar in nature, but we have the first degree variable to be at y. And for what we have in terms of the second problem, we have that dy over dx is equal to 26 minus y. And upon separating the variables and the differentials, we can divide both sides of the equation by 26 minus y and simultaneously multiply by dx, and thus we have 26 minus y as the denominator, dividing into dy, and we have is equal to dx. And so with what we have with the separation, we can now integrate on both sides. So we have for the antiderivative of the reciprocal of 26 minus y. Notice we have a negative y term. So while we have a linear expression taken in reciprocal form, we have not just a natural logarithm but a negative of a natural logarithm, and in this particular case we have the natural logarithm, which can be negative. So we have the negative of the natural logarithm of 26 minus y is equal to x plus c. And if we go ahead and change the sign at both ends, we have the natural logarithm of 26 minus y is equal to negative x, and you can say minus c, but since we're working with a constant, we can just leave that as plus c. And freeing up the 26 minus y, we can use the natural logarithmic base e. So we say we have e to the natural logarithm of 26 minus y is equal to e to the negative x plus c, or you can also say, just being cognizant of the product property of exponents, we write this as e to the negative x times e to the c, and again this is going to be a constant, and so we can say that in the follow through we have e to the natural logarithm of 26 minus y. And so as we look at freeing up the 26 minus y, we have c times e to the negative x, and as we look at isolating the y term, subtracting 26 on both sides, we have negative y is equal to c times e to the negative x minus 26. And if we solve for y, just changing the sign at both ends, and we can leave the c as a positive, or negative c is still going to be a constant. So we can say that in the general solution we had that y is equal to c times e to the negative x plus 26. Now, in the case of what we have for item number 3, okay, we have both variables x and y present along with the differentials dy and dx. And for what we have in this particular problem, okay, we have that, once again, we have that dy over dx is equal to 9x over y. Okay, and as we separate the variables, okay, we have in this one, if we multiply both sides by y, we have y dy is equal to 9x dx. And so for what we have upon separation, we can now integrate on both sides. So we have the integral of y dy, okay, that will be y squared over 2 is equal to 9 halves x squared plus c. And as you look at multiplying both ends by 2, okay, to free up the y squared, okay, we have y squared is equal to 9x squared, and you can say plus 2c, but again 2 times c, since we're looking at multiplying by a constant, we can keep c as a constant, and so in the form of c. And so in terms of solving for y, okay, we can utilize the square root property of equality. So we have for y itself, okay, depending upon the initial condition, okay, y could be equal to positive or negative the square root of 9x squared followed by the constant. Now, for what we have in the case of item number 4, okay, we have in this particular setup, okay, now this can be looked at from different angles. I'll show you one approach. We have in the case of number 4, okay, this time we have 8 plus x squared dy over dx minus 2xy is equal to 0. Okay, now for this one, we can separate gradually the differentials and the variables. And if we move the 2xy over, okay, so we have 8 plus x squared dy over dx is equal to 2xy. And if we separate the variables and the differentials, okay, we can simultaneously divide by y and also by 8 plus x squared on both sides, and also multiply by dx. So if we were to do this, okay, we would have in the setup, we would have dy over y is equal to 2x all over 8 plus x squared dx. And with the separation, we can integrate on both sides. Okay, and so we have the natural logarithm of y is equal to the natural logarithm of 8 plus x squared followed by the constant. And if we work with the natural logarithmic base e, okay, so as to get rid of the natural logarithmic attachments, and again using the product property of exponents, okay, we have e to the natural logarithm of 8 plus x squared times e to the c. And for what we have in the follow through, again with e to the c being a constant, e to the natural log of y goes to y. We can say that we have c, then e to the natural logarithm of 8 plus x squared is going to be 8 plus x squared, and thus we can say that y is equal to c times the quantity of 8 plus x squared. Okay. Now, let me show you another way of doing number 4. Alright, so we have 8 plus x squared dy over dx minus 2xy is equal to 0. Now, this is one where we can use the integrating factor. Okay, but first of all, okay, we have the derivative and we have the linear expression in y, and we want to remove the coefficient in front of the derivative. So we were to divide the equation by 8 plus x squared, and the rewrite, we have dy over dx minus 2x all over 8 plus x squared y is equal to 0. Okay, now in terms of what we have for the integrating factor, okay, we have e to the integral of negative 2x over 8 plus x squared dx, and for what we have in the follow through, okay, we're going to have this equal to e to the negative of the natural logarithm of 8 plus x squared, and we can translate the negative coefficient, say negative of a natural logarithm is going to be e to the natural logarithm of 8 plus x squared to the negative 1, and now we have e and the natural logarithm to cancel each other out, and by then we can say in the follow through that we are going to have the integrating factor to be 8 plus x squared to the negative 1, or in this particular case, we have 1 over 8 plus x squared. Okay, and so for what we have in following through, okay, is that with the integrating factor, if we multiply everything out in the differential equation by the reciprocal of 1 over 8 plus x squared, okay, we're going to have in this one, for the rewrite, we have 1 over 8 plus x squared dy over dx, and you have minus 2x over 8 plus x squared quantity squared y is equal to 0. Okay, again going from this stage to this latter one, and again for what we have on the left hand side, okay, that is going to be the product rule expansion of multiplying the integrating factor 1 plus x squared times y. And again we have this equal to 0, and so for what we have in the follow through is that if we remove the brackets, move the dx over, we have that y over 8 plus x squared is going to be equal to the antiderivative of 0 dx, and so we're going to have y over 8 plus x squared is equal to c, and so as you look at solving for y, we also arrive to the same solution, whereupon we had that y is going to be equal to c times the quantity of 8 plus x squared. Very same solution, and working with the integrating factor.